Let me make a revision of last chapter of semester 1, because what I'm going to teach in this chapter is continuation of semester 1 last chapter. In semester 1 last chapter, we have seen different type of distributions. I will recall all of them. Number 1, discrete uniform distribution. Number 2, Bernoulli distribution. Number 3, binomial distribution. Number 4, hypergeometric distribution. We studied these 4 types of distributions. In continuation of them, we have 2 more distributions in first year. Number 5 is a Poisson distribution, which is on the screen. And number 6 is a geometric distribution. The difference between semester 1 distributions and semester 2 distribution is the range of random variable. Semester 1, I taught 4 different distributions. In each of them, random variable taking a finite values. Whereas in semester 2, I will teach 2 more distributions under the heading of Poisson and geometric. The range of random variable is infinite. That is a basic difference between semester 1 distribution and semester 2 distributions. If you recall your first chapter of semester 1 related with sample space and event, I taught 2 types of sample space: finite sample space and infinite sample space. So if your sample space is finite, the random variable defined on that sample space takes finite values. And with the help of random variable taking finite values, we have studied 4 standard distributions. Whereas another sample space, which is an infinite sample space, we define a random variable x, which takes infinite values. So for such type of random variable, you have 2 distributions. One is Poisson, other is a geometric. Now let me define what is a Poisson distribution. The way of definition is standard, parallel to semester 1. A discrete random variable x is said to follow Poisson distribution if its PMF, probability mass function, is given by, you have a formula for Poisson distribution that is to be remembered perfectly like this: Px equal, this should be small x, because we define P for probability at particular value of x, so it should be small x, equal e raised to minus m, m raised to small x, divided by factorial x. So such function given by statistician whose name was Poisson. So in the memory of Poisson, it is labeled as a Poisson distribution. What is the values for x? X taking value 0, always from begin 0, 1, 2 goes to up to infinity. What is m? M is a constant taking value greater than 0, strictly positive, not equal to 0. If your x not coming from this range, then function will be 0 elsewhere otherwise. So in exam, if they ask, select proper PMF for Poisson, so this function should be remembered properly. How to denote this function by notation? X capital follows. This P is not probability. Now it is initial of Poisson. X follows Poisson with constant known as a parameter m, where m be the parameter of Poisson distribution. What is the concept of parameter? The constant in the function which specifies complete function perfectly. That constant is called parameter. Now on this function, I will put certain remark and then we'll go ahead. Remark number 1, which is very important to study Poisson distribution. We use exponential series to derive many derivations related to Poisson distribution as given below. E raised to m equal 1 plus m by factorial 1 plus m square by factorial 2 plus m cube factorial 3 plus continue up to infinity. You can write this big expression in the form of summation like this. Summation x from 0 to infinity. M raised to x divided by factorial x. Let us check. Put x equal to 0, numerator, denominator. Anything power 0 is 1. 0 factorial is 1. So first term is 1. Plus, that means sigma. Next value of x is 1. Put in the numerator and denominator. M raised to 1 by 1 factorial second term, and so on. So this big expression is written in the summation form like this. What is the clue to remember exponential series? In the numerator, the variable is a power with some constant. And that power is taken in the denominator as factorial. If it is like this, answer of this series, summation is nothing but series. Answer of this series, answer of this sum is e raised to this constant, that is e raised to m. For example, I replace m equal to 2. So 2 raised to x divided by factorial x, summation start 0 to infinity, answer will be e raised to 2. And the expansion will be 1 plus 2 by 1 factorial plus 2 square by 2 factorial plus 2 raised to 3 by 3 factorial and so on. Remark number 2. So this is very important series for a Poisson distribution to be remembered nicely. Real life situations of Poisson distribution. That means in day-to-day life where you can apply Poisson distribution. We use Poisson distribution in real life where the chances of occurrence of an event is very small. In a small time interval is very small. That is, event under study is a rare event. So if you have a rare event, then you can think for Poisson distribution. What are the examples? Number 1, number of defective items found in a lot of good quality. That means we have a production process which produces items with a good quality. That means having a defective is a rare event. So in such situation, you can apply Poisson distribution. Example 2, number of death occurs due to snake bite in a village. Now we are speaking about a village. Village has a huge area. In that village, you are studying death due to snake bite, which is again a rare event. So you can study this situation with the help of Poisson. Third example, number of times system of component fails, and so on. So these are the 3 examples which gives guideline when to apply Poisson distribution. The most important thing to remember is if your experiment provides a rare event, then you can try for Poisson distribution. The Poisson distribution is also useful in the theory of reliability and queuing theory. So reliability is one of the statistical branch. Queuing theory is also one of the statistical branch which based on Poisson distribution. Now we'll try to find what is the mean of Poisson distribution. The Poisson distribution is a model to apply in the real life. So on an average, how many outcomes will be there for your random variable? If I go back, example 1, you are studying number of defective items. So this is your random variable. Number of death occur due to snake bite. This is your random variable. Number of times system component fails. This is your random variable. So you want to see on an average, if you study this process, how many defective items, how many death occur, how many times system fail. The answer will be by calculating mean. That is nothing but mean of your Poisson distribution. Let us see how we do mathematical calculation. Now you know from semester 1 mathematical expectation, and we repeat this for 4 distributions. The same procedure will be continued here. Let capital X follows Poisson with parameter m, then its mean is obtained as below. Mean equal expected value of x, E replaced by summation x into px. This is your definition of mean from semester 1, which is continued here. Now, in this case, the variable begin from 0 to infinity. X as it is, function of Poisson, e raised to minus m, m raised to x, x factorial. To simplify this, step number 1, e raised to minus m is a constant without variable. So you put it outside the summation. Summation x, m raised to x by factorial x. Factorial x can be splitted like this. X factorial written as x into x minus 1 factorial. Now this x cancel with this x. So you get a simplified term. Summation should be for numerator as well as denominator. This is the wrong way of writing. It should be like this. It should be for both. Numerator and denominator both should be covered. So this is not a correct way of writing summation. It should be combined for both. So you can put a bracket like this and then put a summation. So summation should be for numerator and denominator. Be careful. Now I got this simplified term. Just now I told, if you want to apply exponential series, what is the constant in the numerator with the power? That power should be in the denominator. That is not happening here. You can see m raised to x and factorial x is down. So result is this. So I will make adjustment. I will make x as x minus 1 by multiplying m outside. So this m and this m base is common. You can add the power. So m raised to x will be written as m raised to x minus 1 into m. M is a constant. You can put it out. Now, this is exactly your exponential series. What is the power of constant is in the denominator as a factorial. So answer of this is e raised to m. By using exponential series as below. What I quote in the remark, again I have written here. So by this result, answer of this yellow circle is e raised to m. So e raised to minus m outside, this m is there, and answer of this entire yellow marking is e raised to plus m. E raised to plus m, e raised to minus m get cancelled, result is m. So what this derivation teach us? It is useful for your multiple choice question, mean of Poisson distribution with parameter m is coming parameter itself, m. Be remember. We proceed ahead. Variance of Poisson distribution. This everything we did in your semester 1 last chapter. Now, where is the difference? Only your function is changed now. Otherwise, we got mean of binomial, we got variance of binomial, we got mean of uniform, we got variance of uniform. Similarly, we got mean of hypergeometric, variance of hypergeometric, and so on. So the way of derivations are exactly parallel. So this is very easy if you take a help of semester 1 feedback and try to understand your semester 2. Let us proceed. Variance of Poisson distribution. I begin with formula of variance. Variance of x equal to expected value of x square minus square of expectation. This is minus, not 2, not equal. I repeat, variance of x equal expected value of x square minus, this is minus sign, e of x whole square. You can make correction in your notebook, or you can take a pen and paper and write the formula of variance. Expected value of x square minus square of expectation. This is not original. It is simplified. Original variance is expected value bracket x minus ex complete bracket square. And after opening this square, you get this simplified. This is easy for calculation. That's why I take simplified. Now in this formula, we need two calculations. E of x and another is E of x square. But just now we got E of x. This is E of x. Mean equal to E of x. And answer is nothing but m. But expected value of x is m, and expected value of x square. If you recall my words from semester 1, how to write expectation? E replaced by summation always. What is inside? Don't worry. It may be anything. Put as it is inside. Multiply with corresponding PMF. So this is a definition, expected value of x square. Next line, summation as it is, x square as it is, Poisson formula. E raised to minus m raised to x by factorial x. Now, I write x square in the form of factorial. X multiply x minus 1 plus x, curly bracket. So this is completely represent your x square. You can check x multiply x is x square minus x plus x. So this is nothing but x square. Poisson formula as it is. Now what I did, I apply this, I multiply this function for first term. You get this much quantity. Plus x multiply this with summation, second quantity. So expected value of x square is addition of 2. 1 plus 2. But what is 2? It is summation x into px. So answer of 2 is again m. We want to develop only 1. Let us check. Where 1 equal to summation x into x minus 1 e raised to minus m raised to x by factorial x. Again, x factorial written in the form of factorial like this. X multiply x minus 1 multiply x minus 2 factorial. I stop here because I want x minus 1 to cancel in the numerator. That's why I will not go ahead. So this x cancel, x minus 1 get cancel. So you get e raised to minus m constant outside the summation, m raised to x by x minus 2 factorial. Again, if you want to apply exponential series here, the condition of exponential series is the numerator should be factorial as a denominator, which is not happening here. So I will adjust the power of numerator. I did like this, m raised to x minus 2, and this minus 2 cancel with outside m raised to 2. So this is your adjustment. Now you can see this is exactly your exponential series format. So answer of this yellow circle is e raised to m. Therefore, 1 equal e raised to minus m square e raised to m. E raised to m cancel with e raised to minus m. Result is m square. Therefore, we get expected value of x square as 1 plus 2. Answer of 1 is m square, and answer of 2 is nothing but summation x into px. That is a mean, and mean of Poisson distribution is m. Therefore, variance of x, now you can check, formula is very much clear. Expected value of x square minus square of expectation. I got e of x square, that is m square plus m, minus e of x is m whole bracket square. This minus m square and this is plus m square cancel. Result is m. So variance of Poisson distribution again m. So what you understand from these derivations? This is the distribution in which mean and variance coincide each other, and that is equal to parameter of the distribution. So it is only one distribution where mean and variance coincide. Be remember. Remark, for Poisson distribution, we have mean equal to variance equal to parameter of the distribution. For theoretical exam, we can put a question like this. Define Poisson distribution with parameter m. Obtain mean and variance of Poisson distribution. But now you people are going to face multiple choice question exam. So this question is not necessary to worry. But such type of question asked on this topic if there's a offline examination. For online exam, for multiple choice exam, you have to remember this remark. For Poisson distribution, mean equal to variance equal to parameter m. That is to be remembered.